In the silent darkness of the early universe, something impossible was waiting to be seen. Not a galaxy, not a blazing newborn star, not even a luminous cluster stretching across space. Just a faint, stubborn ember glowing red from a time when the cosmos was barely awake. In 2023, the James Webb Space Telescope caught sight of it for the first time. At first, it looked like one of many strange specks scattered through the infant universe, tiny crimson points astronomers had started calling little red dots. But this one, cataloged as QSO-1, refused to fit the script. It didn't behave like a young galaxy. It didn't resemble a dying star. Its light carried a signature that made seasoned researchers pause. Across observatories in Britain, America, and Europe, scientists leaned closer to their screens, staring at spectral lines that shouldn't have looked the way they did. The energy distribution formed a sharp V-shape, a telltale sign that gas was racing at extreme velocities around something incredibly massive, something compact, something powerful enough to bend space itself. For 2 years, teams repeatedly trained Webb's mirrors on these little red dots, capturing their glow across a wide spectrum of wavelengths. Each new dataset sharpened the picture. The gas swirling around QSO-1 was moving fast, far too fast to be explained by a typical young galaxy. Then came 2026. A breakthrough measurement delivered the shock. QSO-1 was a supermassive black hole weighing roughly 50 million times the mass of our Sun. But that wasn't the real twist. The real twist was what wasn't there. Nearly every large galaxy in today's universe hosts a supermassive black hole at its center. Yet those black holes are usually tiny compared to their galaxies, often about 1,000 times less massive than the surrounding stars and gas. QSO-1 broke that rule completely. Its black hole accounted for nearly 2/3 of the total mass in its immediate surroundings. There was barely any galaxy around it at all, no rich stellar population, no heavy elements forged by generations of stars, just hydrogen and helium, the raw ingredients created in the Big Bang itself. It was, in a sense, almost naked. That absence was staggering. Heavier elements like carbon, oxygen, and iron are forged inside stars and scattered when they die. Their absence suggested something astonishing. This black hole may have grown enormous before nearby stars even had time to form. In other words, the monster came first. For decades, astronomers believed galaxies formed first, and their central black holes grew gradually within them. QSO-1 flipped that story upside down. It hinted at a universe where black holes could emerge early, fast, and alone, reshaping cosmic history. If this was true, then our understanding of how structure formed in the universe might need rewriting. And QSO-1 was only one of hundreds of little red dots. The question now wasn't just what QSO-1 was. It was how many more cosmic monsters were hiding in plain sight, and what they might reveal about the universe's first moments. If black holes were forming before galaxies even existed, then what exactly was happening in those first few 100 million years after the Big Bang? And are we ready for the answer? If QSO-1 rewrote the opening chapter of cosmic history, the next discovery threatened to rewrite the entire book. For nearly 3 decades, cosmologists have operated under a powerful assumption that dark energy, the mysterious force driving the universe's accelerated expansion, is constant, unchanging, steady, a silent pressure embedded in the fabric of space itself. That assumption sits at the heart of the lambda-CDM model, the framework that has guided modern cosmology since the late 1990s. When astronomers first realized the universe wasn't just expanding, it was speeding up. But in April 2024, a collaboration of nearly 1,000 scientists working on the dark energy spectroscopic instrument, known as DAISY, announced something deeply unsettling. Dark energy might be weakening. Using DAISY, researchers mapped the precise positions and motions of more than 6 million galaxies, creating one of the most detailed three-dimensional maps of the universe ever assembled. They weren't just plotting dots in space. They were measuring subtle imprints of ancient sound waves, baryon acoustic oscillations, ripples that traveled through the hot plasma of the early universe before atoms even existed. Those ripples left behind a measurable pattern, a kind of cosmic ruler. As the universe expands, that ruler stretches. By tracking how much it stretches over time, scientists can infer how quickly the universe is growing. The early DAISY results hinted that the stretching wasn't behaving exactly as expected. Instead of accelerating at a perfectly steady rate, the expansion appeared to be subtly slowing. At first, skepticism dominated the conversation. It had to. Extraordinary claims demand extraordinary evidence, and the initial signal reached only 3.5 sigma, roughly a 1 in 300 chance of being a statistical fluke. Intriguing, but far from definitive. Then came 2026. With 3 full years of DAISY observations, the galaxy map expanded dramatically, now encompassing roughly 15 million galaxies. Additional datasets were folded in, including supernova measurements and data from the cosmic microwave background, the faint afterglow of the Big Bang. The signal didn't vanish, it strengthened. The statistical confidence climbed to 4.2 sigma, about a 1 in 30,000 probability that the result was random noise. Still shy of the gold standard 5 sigma required to declare a discovery, but close enough to make theorists sit upright. If dark energy is evolving, if it is thawing or changing over cosmic time, then the consequences are enormous. It could mean that Einstein's cosmological constant is incomplete. It could imply that gravity behaves differently on vast cosmic scales. Or it could point toward entirely new physics waiting beyond our current models. For the first time in 27 years, cosmologists aren't just refining numbers. They are confronting the possibility that the foundation itself may be shifting. And if dark energy is truly changing, if the force shaping the fate of the universe isn't constant, then what does that mean for how it all ends? While the fate of the universe was being questioned in deep space, another revolution was unfolding much closer to home, beneath our feet. For most of the 20th century, plate tectonics transformed our understanding of Earth. What once seemed like a rigid shell of rock became something far more alive, a restless engine of shifting continents, rising mountains, and erupting volcanoes. Beneath the crust, the mantle slowly churns. Below that, the outer core swirls as a molten ocean of metal. For decades, scientists believed a sharp boundary separated these two realms. In 2026, that boundary began to blur. Seismic waves from powerful earthquakes have long served as probes into Earth's interior. As these waves travel through different materials, they change speed and lose energy. Deep within the mantle, nearly 3,000 kilometers down, researchers have identified 2 colossal regions, continent-sized structures known as large low shear velocity provinces, or LLSVPs. Because seismic waves slow down inside them, they've often been assumed to be hotter and softer than the surrounding mantle. But when researchers carefully analyzed data from more than 100 major earthquakes, something unexpected emerged. The waves passing through these massive blobs weren't losing much energy at all. Instead of being heavily damped, they retained surprising strength. That detail changed everything. The behavior suggested that the crystalline grains inside these regions are unusually large, and large grain sizes only develop over immense stretches of time. That implies these structures are not recent anomalies, but ancient reservoirs, potentially preserving material from Earth's earliest formation over 4 billion years ago. Then came another breakthrough. By analyzing isotopes in volcanic rocks, scientists searched for traces of ruthenium-100, an isotope that should have sunk into Earth's iron-rich core during formation. Finding it in surface rocks would suggest leakage from the core itself. Evidence began to point in that direction. Together, these discoveries hint that the core and mantle may not be isolated layers after all. Instead, Earth's deep interior could be more interconnected than we ever imagined, with ancient structures acting as stable anchors guiding mantle convection and, ultimately, plate tectonics. And that matters more than it sounds, because without a churning mantle and a dynamic core, Earth might have ended up like Mars, geologically frozen, atmospherically fragile and lifeless. If Earth's core and mantle are quietly interacting beneath us, shaping the planet's habitability, then how many other worlds failed because that connection never existed? Step back for a moment and look at what 2026 has quietly revealed. In the earliest dawn of the cosmos, we may have found black holes forming before galaxies. Across the vast stretch of space-time, we are seeing hints that dark energy, the force steering the destiny of everything, might not be constant after all. And beneath our own planet's surface, Earth's deepest layers appear to be whispering that they are far more connected than we ever believed. These are not minor adjustments. These are fault lines in our understanding. The coming years will determine whether these cracks widen into full scientific revolutions. The James Webb Space Telescope will continue probing the mysterious little red dots, searching for more objects like QSO-1. Each new observation could confirm whether these early supermassive black holes were rare anomalies, or the rule rather than the exception. And then there is LISA, the Laser Interferometer Space Antenna, a future space mission designed to detect gravitational waves from the most massive collisions in the universe. If primordial black holes truly formed in the universe's first moments, LISA may hear their echoes, ripples in space-time traveling toward us from nearly the beginning of everything. Meanwhile, cosmologists are bracing for an avalanche of data. The Vera Rubin Observatory is preparing to observe hundreds of thousands of supernovae, vastly more than ever before. Each exploding star becomes a marker in the cosmic expansion timeline. With that fire hose of information, scientists hope to push the statistical confidence on evolving dark energy past the sacred 5 sigma threshold. If that happens, textbooks will change. And here on Earth, deeper seismic imaging and isotope studies will continue probing the core, mantle boundary. Understanding how long Earth's outer core has been stirring is not just academic curiosity. That motion powers our magnetic field, the invisible shield protecting life from harmful cosmic radiation. It regulates climate stability over geological timescales. It helps explain why Earth thrives while Mars sits cold and silent. What makes 2026 extraordinary is not that we have all the answers. It's that the universe is clearly signaling we've been asking incomplete questions. Science advances not when everything fits neatly, but when it doesn't. When observations refuse to obey expectations, when data unsettles certainty, that discomfort is the birthplace of discovery. We are living in a moment where multiple pillars of physics, cosmic origins, the fate of the universe, the engine of our own planet, are being tested at once. That doesn't mean we were wrong. It means we're getting closer. And if history has taught us anything, it's this. Whenever humanity thinks it understands the cosmos answers back with something bigger. The only question now is whether we're prepared for what it reveals next.